An airplane flies at an angle of with a speed of. If you're taking calculus and you've seen a problem like this, by this point you're probably pretty decent at taking derivatives of functions. But when you see a wall of text like you do with a word problem, what exactly are we differentiating? Related raised problems like these that mention some sort of angle often involve angles of elevation or angles of depression. So let's talk about what these terms mean exactly and how we can turn them into functions that we can work with. So get your pen and paper ready. Feel free to pause this video as you follow along and take notes because we're going to be moving fast. Let's jump in. All right triangles always follow the Pythagorean theorem. But that may not be relevant to the specific related rates problem that you're dealing with, especially the ones that involve the rate of change of angles in the right triangle. Angle of elevation and angle of depression related rates problems make up another very common problem type. Angle of elevation typically describes the angle if you're looking at something above from some distance. Angle of depression is basically the opposite. It's the angle looking down at an object from some distance. Let's take the angle of elevation or angle of depression and call it theta. If theta is in a right triangle, you also have an opposite side to that angle, an adjacent side, and a hypotenuse. And if this made you think of SOHCAHTOA, then you know exactly where we're going with this. The basic trigonometric relations sine, cosine, and tangent allow us to relate side lengths with angles. And when we derive them, we can also see how rate of change of length and rate of change of angle may affect each other. The differentiation of sine, cosine, and tangent functions requires you to know their respective derivatives. If all parts are moving, you also have to apply the quotient rule in deriving these expressions. However, if one or more parts of this problem are constant, the rate of change of those parts will be zero and simplify the process. So now that we understand the nature of this type of problem, let's take a look at the specific example that we saw at the very beginning. But before we jump in, please be sure to hit that like button. And if you'd like to stay in the loop for valuable study tips dropping every week, please be sure to hit that subscribe button as well. Now back to the problem. We like to start off these type of problems by reading the problem and understanding what exactly it says. So let's take a look. An airplane climbs at a 10-degree angle at a speed of 500 miles per hour. Now we can see that this is a two-part problem. Part A asks, how fast is the airplane gaining altitude? And part B starts off by telling us that the current time is noon, the sun is directly above the airplane, and it asks us how fast is the shadow of the airplane moving along the ground. So how do we do this? Let's jump in. We started this problem off by drawing a picture of the plane rising at a 10-degree angle with a speed of 500 miles per hour. We can easily translate this drawing into a right triangle, where we label the angle of elevation as theta, horizontal distance as x, vertical distance as y, and the airplane's overall direction of movement as a. Since the plane is moving, we also label the horizontal speed as dx over dt and the vertical speed or change in altitude as dy over dt. Both of these components together contribute to the overall velocity of the airplane dA over dt. Since we're also dealing with the angle of elevation, any change in angle will be d theta over dt. For this problem, the airplane travels at a constant angle, so this rate of change will be zero. Once we have everything in our diagram, it's time to list out our givens. The only things we're given to work with are the airplane's velocity, the angle of elevation, and the change in angle. Now it's time to start solving. The first part of the problem asks us to find the rate of change in altitude, or dy over dt. To do this, we need to first establish a relationship between the airplane's altitude and our given values of angle and overall velocity. The right triangle we drew shows us that we need to use the sine function. So we write out this relationship as the sine of the angle of elevation is equal to the ratio of the airplane's altitude over its movement. For this problem, we want to solve the expression for y first and derive explicitly. For the derivative, we apply the product rule and chain rule between the airplane's movement and the sine of the angle of elevation. The constant angle of elevation makes d theta over dt 0 and simplifies the derivative expression. After we simplify, we plug in and solve. Once we solve, we want to express the rate of change of altitude as an exact value in terms of sine 10 degrees. And of course, don't forget your units. Part B of this problem asks us to solve for the horizontal speed of the airplane, or dx over dt. Based on the right triangle we drew at the beginning, we know that cosine can relate the horizontal distance of the airplane with its overall motion. So we set up the cosine function and solve for x so that we can derive explicitly again. While we derive, we use the product rule once again and the chain rule, and plugging in our givens simplifies the expression for us since the d theta over dt is still 0. All that's left is to isolate and solve for dx over dt, which we also leave as an exact answer in terms of cosine 10 degrees and include our units. So that wasn't so bad after all. Do you have any other related rates problems that have you stuck? Leave it in the comment below and we'll be happy to help you understand it and point you in the right direction to be able to work it out. Also be sure to check out some of our explanations of other very common related rate problem types, including the ladder sliding down the wall, a person walking into a street light, casting a shadow, and the infamous draining water tank problem. Hope you found this helpful. Until next time, this is Tawheed from Tutelage Tutoring signing off.